Hi, welcome to my channel, Math Made Easy with Laurel. I'm Laurel, and in this video we're going to take a look at related rates. So the area of related rates in calculus is often a very challenging and difficult area for students, and there are a number of reasons for that. Probably the main reason is because in a lot of the questions that you're going to see in related rates, you will not be given the equation. You will be given it a word problem, and you're going to have to come up with the equation that you're going to have to differentiate. So you're going to be using prior knowledge in areas of trigonometry and geometry and some other areas. And I will try to do examples that cover a lot of the typical related rates questions that you will see, and you'll start seeing some similar patterns. Another reason that related rates is challenging is that you will be given an equation in terms of whatever variables, and you'll be asked to find time rates of change of those variables. So we've differentiated with respect to time before when we were given a function of time. So if we had displacement as a function of time, that was straightforward. That was just like differentiating with respect to x when we had y in terms of x. So the derivative of s with respect to t here will just be 6.4t plus 7. However, with related rates questions, you're going to be given other variables and understand that they are changing with time. So you're differentiating, you're finding the rates of change with respect to time. So for example, if I had y as a function of x, we know how to differentiate y with respect to x. That's not an issue. But with related rates, instead what you're going to be doing is differentiating this whole equation with respect to time. So you're going back to the chain rule. You're going to do the same thing that we did in implicit differentiation. Understand that every variable you see, if it's not a constant, then it's a function of time, and you're differentiating with respect to time, so you need to use the chain rule. Let me show you. If I was asked to differentiate this with respect to time, I would have dy dt, and use that notation. Don't use y prime here because y prime would indicate or suggest that you're differentiating with respect to x, and that's not what we're doing. So dy dt will equal, we differentiate each term with respect to time. So the derivative of 5x cubed would be 15 x squared and then dx dt. Remember, x is a function of time, so we have to multiply by the derivative of x with respect to time. Same thing with the next term. The derivative will be 6x times dx dt. Because x is a function of time, so I'm using my chain rule, I can't forget dx dt. Plus, the derivative of 7x will be 7 times the derivative of x with respect to t. So even though t is not even in the function, we're differentiating with respect to it. And then you're going to need to know more than just your variable values. You're going to need to know, if you, for example, wanted to find dy dt, you would have to know dx dt, as well as the x. So it does get tricky, but the thing to remember is differentiate with respect to time and treat each variable as a function of time. Use your chain rule. Let's take a look at some examples. In our first example, it says a snowball is brought inside and starts to melt. How fast is the snowball shrinking when the radius is 2.5 centimeters and the radius is decreasing at a rate of 1 millimeter per minute? So we're talking about the size of the snowball and the radius. Both of those things are changing with respect to time. So we need to first of all get a relationship between the size of the snowball and the radius, and that would be volume. The size of the snowball is going to be volume. We're talking about volume of a sphere. So volume will equal 4/3 pi r cubed. That's the formula for volume of a sphere. Let's also write down the things that we know. We want to know how fast the snowball is shrinking. So what we're finding is the rate of change of the volume. That will be our unknown. So we're finding dv dt. How fast means with respect to time. And it tells us that the radius is 2.5 centimeters. And it tells us that the radius is decreasing, so that's the rate of change of the radius with respect to time. If it's decreasing, that will be a negative 1 millimeter per minute. We have a problem before we even start. If our radius is in centimeters and our rate of change of radius is in millimeters per minute, it's not going to work. You have to be consistent with your units. So you could either change this to centimeters per minute, or you could change this to millimeters. I'll just change this to millimeters. And if you were working with imperial units and you were working with inches, again, just as long as that was in inches and that was inches per minute, you would be fine. So now we differentiate with respect to time. So we're going to have dv dt. This is our constant times r cubed. So I would have 4/3 pi times the derivative of r cubed with respect to time will be 3r squared times dr dt. So whatever the variable is, when you differentiate it, you should have that variable over dt. We could clean it up first and then we could put our values in. The 3's will cancel, so we'll have 4 pi. R is 25. dr dt is -1. And when we calculate this, we should get a value of -7,854. Now my unit, if I had millimeters for my radius, when I square it I get square millimeters, and here I have millimeters per minute, so the millimeters will multiply and I'll get cubic millimeters per minute. So the volume is decreasing at a rate of -7,854 cubic millimeters per minute. And that makes sense because volume should be measured in cubic millimeters. If you did this in centimeters, you would get -7.854 cubic centimeters per minute. So there's lots going on. Remember to differentiate with respect to time. Figure out what rate of change you want to find and which one you're given. Sometimes you'll be given more than one, which we'll get to later, and any other values that are given. Make sure your units are consistent, and then put those values in after you differentiate. Let's take a look at another example. Okay, our next example talks about a 5-meter ladder leaning against a wall. So we can make a little drawing. So here's our wall, and we've got a 5-meter ladder leaning against the wall. And it starts sliding down the wall at a rate of 0.5 meters per second. How fast is the bottom of the ladder sliding away from the wall when it is 2 meters from the wall? So we're dealing with this distance here, which I'm going to call A, and this distance here, which I'm going to call B, and this is a constant distance of 5. This is a right triangle, so the relationship that we're going to use to get an equation between A and B is the right triangle theorem. So we've got A squared plus B squared will equal C squared, but C is a constant value of 5. Now let's determine what rate of change I need to find and what rate of change is given. So it tells me that it's sliding down the wall at this rate. So that means I know how A is changing. So dA dt will be equal to. So A is changing. If the ladder is sliding down the wall, A is decreasing, and we indicate that with a negative. So this height or this length is decreasing at a rate of -0.5 meters per second. It says how fast is the bottom of the ladder sliding away from the wall. So we want to know how fast B is changing. So dB dt is what we want to calculate. When it is 2 meters from the wall, so when B is 2 meters. We're now going to differentiate this with respect to time. So the derivative of a squared will be 2a dA dt, plus the derivative of b squared with respect to time will be 2b dB dt, equals the derivative of 25 is 0. I want to solve for dB dt, so I'm going to move this term over. So 2b dB dt will equal negative 2a dA dt. And I like to isolate my variable and then plug the values in. So I'm going to have negative 2a divided by 2b times dA dt, and the 2's will cancel. So dB dt will equal negative a over b dA dt. Let's plug my values in. Now I don't have a. However, I could find a when b is 2 by using my right triangle theorem. So a squared plus 2 squared will equal 5 squared. So a squared will equal 25 minus 4, which is 21. So a will be equal to the square root of 21. So I plug my values in. A is negative square root of 21. B is 2. And dA dt is negative 0.5. When we calculate that, we get positive 1.146. Now my unit should be the rate of change of B, which is in meters, per the time factor, which is seconds. So as the ladder is sliding down at a rate of 0.5 meters per second, the bottom of the ladder is sliding out at a rate of 1.146 meters per second. With a lot of these questions, I'm not concerned about significant digits, so I often round off to the nearest millimeter. But if you're asked to pay attention to significant digits, you might need to be a little more particular about your rounding off than I am. I want to continue with more examples of related rates, and I will do that on the next video. So take care, and we'll see you then.